Okay, so the first two lectures, I first told you about how you can use optical methods to measure blood flow, and then yesterday I was telling you about how you could use optical methods to study neurovascular coupling. Today I want to tell you about, again, functional brain imaging, and really using optical imaging to help us gain more physiological insight in understanding the bold fMRI signals. So as many of you or most of you probably know, functional magnetic resonance imaging has really revolutionized human functional brain imaging by providing just amazing maps of brain activity under many different stimulus conditions. It's teaching us a lot about the interactions of different brain regions, but you know, its interpretation is complex. It's not measuring neural activity directly, it's measuring it indirectly. It's measuring deoxyhemoglobin, because deoxyhemoglobin is paramagnetic. But you know, how does that really relate to neural activity? That was the discussion yesterday, right? This neurovascular coupling. So we get a vascular response, which is modulating deoxyhemoglobin, which is what we're measuring with fMRI. How do we actually quantify that? So I want to delve into that more deeply today. And along the way, you'll just see the tremendous power of being able to span multiple length scales with optical imaging technology that really leads to a lot of scientific discovery as well as translation and applications. Okay, so like yesterday and the day before, I'm going to be describing the utilization of optical methods in humans and animals, and with volumetric imaging in animals, and how we bring all of that data together to address, you know, complex questions. So the complex question we're going after today is bold. Bold is complex. Bold is what fMRI measures. It's the blood oxygen level dependent signal. And basically, it arises from deoxyhemoglobin, because deoxyhemoglobin is paramagnetic, oxyhemoglobin is diamagnetic. So basically what that means is oxyhemoglobin in a magnetic field, nothing happens, but if you have deoxyhemoglobin in a magnetic field, it actually responds to that and perturbs the magnetic field. So it produces magnetic dipoles around the deoxyhemoglobin molecule. fMRI essentially is measuring, or MRI in general, is measuring the dephasing of the magnetic moments of essentially protons, water molecules in your body, right? And so those magnetic moments are aligned with an RF pulse, and then they attenuate, they decay back to the main magnetic field direction of the big magnet that you're sitting in, and that realignment with the magnetic field is a precession of the magnetic moment around the main magnetic field, and that precession can dephase, and it dephases based on heterogeneity in the magnetic field. And that heterogeneity is arising to a large part by deoxyhemoglobin. And so you can have deoxyhemoglobin in a venule, you can have deoxyhemoglobin in a capillary, or you can have it in a large vein, right? And so those are different size scales, and kind of the spatial scale of the perturbation in the magnetic field is going to be dependent on the size of the blood vessel. And also it's dependent on the length scale in which the proton, the water molecule, is diffusing during the time scale of the dephasing that is measured by MRI. And so this is kind of shown, a water molecule here is diffusing around a small venule. And it's not going to, you can see another diagram here, this is, say, around a capillary. You can see this diffusing water molecule is going to be probing a lot of different phase variation in the magnetic field, whereas in a larger vein, it's not going to see so much. So you begin to get the idea that there's a very nonlinear effect in the bold signal. It depends whether or not that water molecule is diffusing around a small vessel with a lot of deoxyhemoglobin or a large vessel with no deoxyhemoglobin, right? These have big effects on what the bold signal is actually measuring. And the relaxation rate of the spin that's precessing, you know, will, to a large degree, will be linear around large vessels, or it could be quadratic around small vessels. And people have investigated this. I need to point out that actually, so this is the bold fMRI signal is measuring deoxyhemoglobin, right? But neurovascular coupling causes changes in blood volume through arterial dilation, which then modulates blood flow, right? If you change blood volume, if you increase blood volume, that's increasing deoxyhemoglobin, right? But if you increase blood flow, that actually washes away deoxyhemoglobin, right? So both of these effects are happening. You have an increase in blood flow, which decreases deoxyhemoglobin. You have an increase in blood volume, which increases deoxyhemoglobin, right? So these are competitive effects. So it's very complex. Not only is the bold signal linearly dependent on the amount of deoxyhemoglobin, but the neurovascular coupling is pushing deoxyhemoglobin in both directions, right? So it's very complex understanding this. People have done this, studied this since the advent of bold fMRI for measuring brain activity in the 90s, but they were using simple Monte Carlo simulations of water molecules diffusing around simple cylindrical models of the microvascular network, right? So it's a very oversimplification. So what we wanted to do was actually use all of our optical measurements, which allows us, as shown you in the past days, to measure microvascular networks on a very small scale and really build up a ground truth model of a bold fMRI voxel, right? But at the same time, we were using near-infrared spectroscopy combined with fMRI to help us gain more physiological insight at the macroscopic scale. So let me start by telling you that. This was work that Ted Huppert did with us when he was a student with us, and actually Rickson, when he was visiting us in Boston for a year, he was involved in some of these experiments. So Ted Huppert started these experiments, and it's very easy. FNIRS, I was telling you about it yesterday, we're putting a near-infrared light into the head, it diffuses through the scalp and skull into the brain, interrogates the amount of hemoglobin, and by using different wavelengths of light, we can monitor the relative changes in oxy and deoxyhemoglobin. This is all done with glass and plastic fiber optics that doesn't interfere with the magnetic field, so it's very easy for us to do the FNIRS and the MRI at the same time. So in this experiment, Ted had his subjects tap their fingers for 2 seconds, and we measured the hemodynamic response in the motor cortex with the FNIRS and the MRI simultaneously. So this is an average over 5 subjects, and you can see basically this rapid increase in oxyhemoglobin and total hemoglobin, and this delayed decrease in deoxyhemoglobin. This is all measured with near-infrared spectroscopy from the motor cortex here. And at the same time, we get the bold measurement. So I'll normalize all of this right now, and you can see that the deoxyhemoglobin and a bold signal agree with each other very well, right? So this is what we expected, them to be temporally correlated like this. Ted also, and I'm not going to show you, did the spatial correlations here, so we also see very good spatial correlation between the FNIRS measurement of deoxyhemoglobin and the bold fMRI measurement. So this was all a very nice cross-validation of near-infrared spectroscopy against fMRI, giving us just more confidence in the physiological interpretation of the bold signal, right? But can we do more, right? Yes, we can do more, and we can measure the cerebral metabolic rate of oxygen, maybe try to get a little bit more close to the underlying neural activity, right? So as you saw, the hemodynamic response is a complex indirect measurement of neural activity because you get a blood volume change, you get a blood flow change, this washes out deoxyhemoglobin, washes in oxyhemoglobin. Maybe a metabolic measure will be more closely coupled to the underlying neural activity. And so we can measure the cerebral metabolic rate of oxygen quite simply. If you could just measure the oxygen flowing into a region of tissue, the oxygen flowing out, well, the difference is the oxygen that has been extracted into the tissue and consumed by the tissue, right? So that will be a metabolic measurement of the consumption of oxygen. To do that, we really just need flow times arterial oxygenation and flow times venous oxygenation. So we can measure that. We can measure blood flow, and we can measure the hemoglobin oxygenation. The standard way of measuring oxygen consumption is with positron emission tomography. It's actually you can have radioisotopic oxygen. It's very difficult. It has poor spatial and temporal resolution, and only a few sites around the world actually perform this. If you could get 017, you could actually do MR spectroscopy. This is a very nice way to measure oxygen consumption, but it will cost you about $2,000 per measurement because 017 is very rare and very hard to get. So people have been trying to develop other methods. MRI, people are working really hard. We have very nice MR measurements of blood flow. People are trying to develop MR measurements of the oxygen extraction fraction. These methods are still being developed so to try to get baseline measurements of oxygen consumption, but instead we could look at evoked changes in oxygen consumption. So we could just do some algebra here and say, what are the changes in oxygen consumption? Well, the changes in oxygen consumption are related to the changes in blood flow, changes in deoxyhemoglobin, and changes in total hemoglobin concentration. And actually, since the late 1990s, people have used fMRI measurements of blood flow with arterial spin labeling. They have to calibrate the bold signal to get a change in the relative changes in deoxyhemoglobin, and they make an assumption about the relationship between blood flow and blood volume or total hemoglobin concentration, and they make estimates in of the evoked changes in oxygen consumption. But it requires you to calibrate this bold fMRI signal. Because bold doesn't give you this directly, it gives you something proportional to that, so you have to calibrate that. With the optical methods, we get an independent measurement of the deoxyhemoglobin that we don't need to calibrate. We also get a measurement of the change in total hemoglobin concentration. We could also measure blood flow. So if we combine MR and optical together, we get good spatial resolution measurements of the brain activity with fMRI, and we get good temporal resolution measurements with near-infrared spectroscopy. Actually has better temporal resolution than fMRI. And we get calibrated measurements of deoxyhemoglobin, but we also get total hemoglobin concentration changes. So we can now take these combined measurements, the NIRS measurements and the fMRI measurements, and we can fit the data with a biophysical model of oxygen delivery to the tissue. So we can fit the data very well, and from that model fit to the data, we get an estimate of the evoked response in the cerebral metabolic rate of oxygen, right? So this really gives us unprecedented spatial temporal resolution measurements of the evoked changes in oxygen consumption during the brain activation, right? So there's no other method out there that allows you to measure oxygen metabolism with such high spatial and temporal resolution in humans. And so we get very precise measurements of it, and very interesting physiology comes out of this as well. A common parameter to look at is actually the flow response relative to the oxygen consumption response. This was long debated. Why is it that the flow response is always 2 to 3 times greater than the oxygen consumption response? Very interesting physiology that's actually related to the fact that oxygen needs to diffuse from the capillaries to the mitochondria. That diffusion happens down a concentration gradient, and the only way you can get oxygen to diffuse faster is to raise up capillary oxygenation higher, right? And the only way you can get the capillary oxygenation to go higher is if the blood flow response is greater than the oxygen consumption response, right? So it's really quite simple. So I was really excited about this many years ago when we first developed it, and I thought it would just revolutionize fMRI, functional brain imaging. We'd just always combine FNIRS with fMRI, and it would solve all of our problems. Well, it turns out that's kind of hard to do, and nobody else has done it except a few other groups like us. So I was wondering, well, what else can we do with it? Since combining FNIRS and fMRI is actually routinely very difficult to do. Well, what we could do is maybe just gain more confidence in the fMRI-only measurement of getting estimates of oxygen consumption. So if you want to use only fMRI to estimate changes in oxygen consumption, you have to calibrate the bold signal. And the way people do that is you can write down this fMRI equation that relates oxygen consumption with blood flow in bold. And you have this calibration parameter M, which relates bold with deoxyhemoglobin. To calibrate this, they usually do a hypercapnic experiment, so they have their subject breathe CO2, and that CO2 will cause blood volume to increase without changing oxygen consumption. So oxygen consumption, there will be no change in oxygen consumption, but it's going to produce a change in blood flow. It's going to produce a change in BOLD. And so then we could solve for M, right? And so solving for M, we make those measurements of BOLD and blood flow changes, easy enough. But you have these other two parameters, beta and alpha. Beta is related to the effect that deoxyhemoglobin has on the perturbation of the magnetic field. So this is a physical quantity. And alpha is actually a physiological quantity, which is this relationship between the change in blood volume and the change in blood flow. Right? Because remember, with fMRI, we're not measuring changes in blood volume, so we have to make an assumption there, and it's related to the changes in blood flow. And this alpha parameter is something we'll come back to later on in the talk. Okay, so can we use these data here to gain confidence in this hypercapnic calibration, right? So this was something that people in the fMRI community are using, but there's lots of literature saying, well, it works, or no, it doesn't work, well, maybe it works, well, maybe it doesn't work. So we wanted to use a fusion of FNIRS with fMRI to help us understand, is it working? And so Miriam Yusel was doing this work, and so with the optical imaging, we do an image reconstruction, which is a linear inverse problem, and we can take measurements of the changes in the measured intensity at 830 nanometers, at 690 nanometers. We relate that to a spatial map of the hemoglobin concentration changes, and so then we have to solve this inverse problem to solve for that map of oxy and deoxyhemoglobin. This is an ill-posed problem. We have to regularize it. It does not have good spatial resolution, right? If we have measurements by fMRI, BOLD measurements and ASL measurements, that has very good spatial resolution, actually. And the BOLD is a simple identity relationship, right? It gives us the spatial map of the deoxyhemoglobin changes. The problem is we don't have this proportionality constant, this calibration coefficient. So we want to solve for that. Blood flow is just related to the changes in total hemoglobin concentration. So we could use the blood flow measurements by fMRI to spatially constrain our images of total hemoglobin concentration. Again, it's just an identity relationship. Okay. So Miriam did measurements in 8 subjects and did the BOLD calibration and did the fusion measurements. So with this fusion imaging method, we could get these images of oxyhemoglobin and deoxyhemoglobin in the 8 subjects, and at the same time, we're calibrating this M coefficient. And you can see M is varying from 0.03 up to 0.11. So this was already quite interesting to us because you can go back in the literature and find papers saying, well, M has a value of 0.1 all over the brain for all subjects. I'm like, well, no, it doesn't. It depends. M depends on the blood volume fraction, and we know that varies all over the brain, right? M also depends on the oxygen extraction fraction, which could also be varying across the brain, right? So it was no surprise to us to see this large variability. But we wanted to compare it with the hypercapnic calibration, which is the standard way, and we were very pleased to see that there's a very strong correlation between the standard MR measurement of calibration against our fusion model, right? So this is giving more confidence in just using fMRI and hypercapnic calibration to calibrate your BOLD fMRI signal, right? But what we're really interested in doing is estimating evoked changes in oxygen consumption, right? So we could measure changes in oxygen consumption using just fMRI, or we could use our fusion model to estimate changes in oxygen consumption. Here again, we saw a very good linear relationship, which was encouraging, but if you notice, the slope is actually not 1. So fMRI would measure, say, a 40% change in oxygen consumption when the fusion model will measure a 50% change in oxygen consumption, right? So the slope is about 0.9, which suggests that maybe there's something wrong with the way fMRI calibration of fMRI is fine, but then the model you use to calculate the changes in oxygen consumption, there's something wrong, right? So what could that be? We're going to have to delve a little bit more deeply into that. It is comforting, though, that Rick Buxton, who has studied and modeled fMRI signals for a very long time, he wrote a modeling paper in 2011 that essentially predicted the same thing, that if you use a standard Davis model, as it's called, to analyze the bold fMRI signal, you're going to estimate the true changes in oxygen consumption chain, right? So how are we going to get to the bottom of this? We're going to get to the bottom of this by turning to microscopic measurements, using all the tools I've described to you the last 2 days and some new ones I'm going to tell you about. And we want to make measurements of oxygen delivery and oxygen consumption at this microscopic scale and really build a model of an fMRI voxel, right? So here's an fMRI image of changes in brain activity in a rat, but we're going to go in there with microscopy, right, and measure deoxyhemoglobin in all of these blood vessels. This essentially represents a single voxel of fMRI, right? So a single voxel of fMRI is very complex in that it contains thousands of blood vessels, all with different amounts of deoxyhemoglobin, right? And so we're going to probe this. We're going to measure blood flow using laser speckle methods and OCT, as I was describing to you. We're also going to introduce this novel phosphorescent dye that is quenched by oxygen. This allows us to map oxygen throughout all of these blood vessels, right? And we're going to take measurements of the arterial dilation changes with two-photon microscopy, and then we can basically put all of this into a model of oxygen advection and diffusion throughout this fMRI voxel, and we can calculate this oxygen diffusion and delivery throughout the tissue, right? And then ultimately, we will have deoxyhemoglobin at every point in the tissue, at every point in time, which then allows us to simulate the perturbation of the magnetic field and the effect that that has on the MRI signal, okay? So it's a very complex model, but we succeeded, and so I'm going to tell you about that over the next 20 minutes. Okay, so to do this, we had to build a multimodal microscope that Sava Sakadzik and Abbas Yassin spent several years building. They affectionately called it Octopus because it had it was multimodality. It had 8 different components to it. So Octopus, though, stood for Optical Coherence Tomography Oxygen Pressure Microscope. I thought that was very clever of them. But it combines OCT, two-photon microscopy, confocal microscopy, laser speckle contrast imaging, and a few other things. Okay, so the first thing we wanted to do was use this to measure the partial pressure of oxygen throughout the microvascular network. So when we started this project, the way you would measure oxygen at a point in the tissue was you'd take an electrode, you'd stick it into the brain, the electrode would have a coating on it that would be sensitive to the partial pressure of oxygen, right? And so that would allow you to measure oxygen at one point in the brain. If you wanted to measure at another point, you'd remove the electrode, you'd stick it in another point in the brain, right? So you can't really make many measurements of the partial pressure of oxygen. If instead we had a dye that Sergei Vinogradov had just made, which is a beautiful dye in that it's very well encapsulated, which calibrates the relationship between phosphorescence lifetime and oxygen very well, but importantly, it has these antennae out here that have a very strong two-photon cross-section that then transfer their excited state electron to the porphyrin or palladium, he uses both actually, core that gets into a forbidden state and so produces the phosphorescent decay. But if an oxygen molecule comes around, it can steal the excited state electron and essentially quench that phosphorescence, shortening the lifetime. Right? So this is showing just a fluorescent image of the vasculature. If we now project it over depth, but if we now look at the phosphorescence image just at a single depth, this is 150 microns deep, we can pick out this venule and this arteriole, and then we can go in and just measure the phosphorescence lifetime in the venule and in the arteriole, and you can see the arteriole has a faster phosphorescence lifetime than in the venule, and that's simply because there's much more oxygen in the arteriole, and that oxygen is quenching the phosphorescent state of this molecule, right? And so it's well calibrated. We can go from lifetime to the partial pressure of oxygen, right? So here we did it at 2 points. This is two-photon microscopy, right? So we're not sticking an electrode into the brain. We just have to raster scan our focus to different points in the tissue. We can focus at different depths, and very efficiently we can map oxygen at hundreds of points throughout the tissue. So this was the first time we did it. You can see many points of oxygen. We went through this very painful process of graphing this microvascular network, and once we've graphed that microvascular network, we could then take these point measurements of oxygen and interpolate them throughout the vasculature, which then allows you to make really nice visualizations like this. This was the first one we did. So we thought this was incredibly cool. You could actually see an arteriole on the surface of the brain with high partial pressure of oxygen. You could follow it descending through a penetrating arteriole into the cortex, branching into capillary networks, losing oxygen all along, and then rising up through a penetrating venule again to a draining vein on the surface, right? This was the first one we did. We've subsequently gotten much better at it. We can really map this out in incredible gory detail. And one thing that I find fascinating, and if you stare at this, you can see it quite evidently, the partial pressure of oxygen in the capillaries is actually much lower than the partial pressure in the veins, right? So this really confused us for about 18 months because we were physicists, and physicists like spherical cows and simple things like that. We think of blood flow as being an artery, a capillary, and a vein. So you'd have high oxygen, lower oxygen, and lower oxygen. Conservation doesn't allow you to have high oxygen in an artery, low oxygen in a capillary, and then high oxygen in a vein. How can that happen, right? It makes no sense. But actually, the topology of the vascular network, of course, is not that simple. There's a network of blood vessels, and you can actually see the answer in this image. You can see there are some capillaries that have shortcuts from the arterioles to the venules. So here's one, there's another one, right? And those are capillary thoroughfares that carry a lot of oxygen. There's high blood flow. And they're essentially shunting oxygen from the arterioles to the venules, right? The vast majority of capillaries don't have high blood flow, and they're kind of delivering all of their oxygen to the tissue, right? So you might ask, well, why are these capillary thoroughfares? And we have a hypothesis, we haven't proven it yet, but this is a very efficient way of delivering more oxygen to the tissue in times of need. All you would need to do is take these two capillaries, squeeze them a little bit, and then suddenly blood flow would reduce in those capillaries and send that oxygen out to all of the other capillaries, right? So we just need to identify the mechanism by which that could happen, and maybe if there's time, we'll discuss that later. Interesting potential for a novel mechanism of oxygen reserve in the brain. An interesting thing about the brain, if you don't know, there's actually no oxygen reserve, right? So the brain is consuming pretty much all of the oxygen that's being delivered. If you shut off blood flow to the brain, you'll pretty much pass out in seconds because there's no oxygen reserve, right? The other organs can survive much longer without oxygen, but the brain can't. You would think the brain would have developed some novel ways of providing a reservoir of oxygen, right? So we would like to discover what those reservoirs might be. So Sava Sakaznik has worked very hard on this. I showed you one example. You know, he exhaustively repeated this on 6 animals. So we have these microvascular networks from 6 different animals. This is just showing you arteries in red, capillaries in green, venules in blue. Each one of these you could think of as a voxel for an fMRI measurement, right? So he went in and measured oxygen in all of these vessels, and so then we can look at the summary statistics. You can quantify, so we measure the partial pressure of oxygen, but you can always convert that to a hemoglobin oxygenation by using the Hill equation. So we like to look at it in terms of the hemoglobin oxygenation. Because this is the quantity of oxygen. This relates more directly with the quantity of oxygen that is being delivered to the tissue and is being consumed by the tissue. So we can look at the hemoglobin oxygenation for different diameters of arterioles and different diameters of venules. And several things come out of this graph. First of all, you know, as we go to branches to smaller and smaller arterioles, you see there's less and less oxygen. And you know, we already, basically what we're seeing is 50% of the oxygen delivered to the tissue is actually coming from the arterioles, before you ever get to the capillaries, right? So if you read textbooks, it says oxygen is delivered to the tissue from capillaries, right? So that's the standard textbook explanation. But actually, if you look at your arterioles, you'll see that arterioles are giving up oxygen to the tissue as well, right? It's not just the capillaries. So this is something that actually physiologists have known for decades, that in fact arterioles do deliver oxygen to the tissue, but nobody ever actually quantified how much oxygen is delivered to the brain from the arterioles. And so these data show that basically all you need to look at is this is the amount of oxygen entering the brain region, this is the amount of oxygen leaving the brain region, and by the time we get to the capillaries, we've already delivered half of that oxygen to the tissue, right? That seems strange. Why is that happening? The other thing you'll notice is in these venules, the smallest venules have very low oxygenation, and as you go to larger and larger venules, oxygenation goes up, right? So this is where we as physicists were very confused. Where is this oxygen coming from, right? But I already explained that to you, where that's coming from. That's you know, coming from this complex topology of the microvascular network, where we have some capillaries with high flow that have high oxygenation, right, that are raising up this oxygenation as we drain into larger and larger venules. So how about how about the oxygenation of the capillaries? You know, so now we're just looking at the distribution of the oxygen saturation in the capillaries. You know, here's the venous PO2 of the draining vein, 62%. This is remarkably consistent across length scales, across species. If you measure venous oxygenation in humans and animals, it's always between 60 and 70%. It's really quite remarkable. Also in disease states, it's always amazingly around 65%. And we've done it microscopically, and we looked at the smallest venules and the largest venules. It's always around 65%, right? So there's this amazing regulatory mechanism somehow that's making the venous saturation always around 65%. Despite that, however, you look at the capillaries, the vast majority of capillaries have a hemoglobin oxygenation well below that, right? So this was amazing to us. And it's just the few capillaries that have high oxygenation that kind of raise up this oxygenation in the venules, right? All right, so I've already discussed this. So, you know, this is related to, I've been saying there's these capillaries with high flow. Well, can we measure flow? And so I showed you 2 days ago and yesterday we can use OCT to measure flow. And I'm not going to dwell on this again, but importantly, you know, we've made measurements of flow in these microvascular networks, and we can now take all of this information. We have these graphs of the microvascular networks. we've measured blood flow, we can calculate blood flow, right? And we calculate blood flow, and then we can compare our calculations of blood flow against the measurements of blood flow, and we get very good comparison there. So we're beginning to develop a model, really, of the fMRI signal, right? We need to calculate blood flow everywhere, and we can validate the model against our measurements. So we're getting good validation there. And so that's, modeling blood flow is easy. That's just a circuit equation. Modeling oxygen delivery is much more complex. First of all, you have oxygen flowing through the blood, so that's advection of oxygen through the blood. But it's also diffusing from the blood into the tissue. So we have to solve the diffusion equation. So this is an integral differential equation we use finite element methods to solve. You could also use Green's function methods to solve this. And this was an early calculation I did. This is just showing a bolus of oxygen being delivered into the cortex and diffusing into the tissue, right? So this is what we want to do, but not on this toy problem here, but we want to do it on a whole MRI voxel that's 500 microns by 500 microns by 500 microns that will have 1,000 or 2,000 capillary segments, right? So we are now going to simulate the oxygenation, so we can do that simulation, right? To do the simulation of oxygen delivery, we of course need the blood flow measurements and simulations, and I showed you we already validated that. So we have the flow measurements, which then allows us to simulate oxygen delivery. Now we've simulated here the oxygenation throughout the microvascular network, but remember we've also measured oxygenation throughout the microvascular network. So we can now validate whether or not our model is accurate. And so we compare those for different branch orders of arterioles and venules, and we see good agreement between the simulations and the experiments, right? So we're validating the model each step of the way. So this gives us confidence in our model. But now we want to look at brain activation, right? So during brain activation, we're going to get changes in oxygenation. Those changes in oxygenation are going to arise from arterial dilation. And when there's an arterial dilation, blood flow is going to change, which is going to just deliver more oxygen to the downstream blood vessels. And so we can measure the arterial dilation at different branch orders of the arterioles. Anna DeVore did this very exhaustively. We put those diameter changes into our model of blood flow and oxygen advection diffusion, which then allows us to calculate, this spatial distribution of the spatial temporal changes in oxygenation. From that simulation, we can then measure from the simulation what are the changes in oxygenation in the arterioles versus the capillaries versus the venules. And experimentally, we've also measured this with the PO2 method using confocal microscopy. We've measured the oxygenation changes in the surface arteries and the surface venules. And so this is what it looks like during brain activation for the surface arterioles experimentally and for the surface venules. So we measure that change in delta PO2, and we compare it with the simulations, and we have very good agreement between the simulations and the experiments. Okay? So it's giving us more confidence in our model. Now, from the model, we now know what the deoxyhemoglobin content is at every micron in this voxel at every point in time. We know the amount of deoxyhemoglobin. We can thus calculate the perturbation to the magnetic field using this convolution operator. And when we have the perturbation of the magnetic field, we can then simulate the diffusion of water molecules around that perturbed magnetic field, right, like this, using Monte Carlo simulations. We accumulate the dephasing of the magnetic moments of those water molecules during different MR pulse sequences, which then allows us to simulate what are the changes in the a gradient echo bold signal or the spin echo bold signal. So these are the predictions. Anna DeVore then went and made measurements using the same experimental conditions, made fMRI measurements in the rat during 4-pulse stimulation. This stimulus is presented here. A few seconds later, you see the change in the bold signal. She could analyze the bold signal at different depths. And there we have our bold signal change, and we compare that with the simulation and got good agreement. Okay, so we're very happy. we've validated this bold model at each step of the way. And so we have a validated model. Woohoo, we're good modelers. But a model is only useful if it makes predictions that teaches you something new about the experimental system, right? So we wanted to begin to look at some things that are difficult to measure experimentally. And so the first thing we looked at was actually what is the contribution of different vascular compartments to the bold signal, right? So arteries and veins have different amounts of deoxyhemoglobin. Veins have a lot more deoxyhemoglobin. So you expect veins to contribute much more to the bold signal. This is what everyone's always expected. And there's a partitioning that people have assigned to veins versus capillaries versus arteries that were based on simplified models of the vascular network, basically just cylinders, right? But we know the vascular network is much more complex, and so we set out to investigate in a realistic model, what is the contribution of each vascular compartment for gradient echo MR sequences and spin echo MR sequences, and basically got results that agreed really quite well with what people had expected from the simplified models. So we didn't learn much there, but we did observe something curious. You can have, the magnetic field has an orientation, right? So the magnetic field could either be perpendicular to the surface of the brain or parallel with the surface of the brain. So why would that make a difference? Well, the vascular architecture of the brain is quite interesting, right? All of the blood is pretty much delivered to different regions of the brain from the surface of the brain. You have large arteries on the surface of the brain. They branch into smaller arteries that then dive into the cortex, branch into capillary networks that then collect and ascend back to the surface of the brain in venules and then drain on the surface of the brain in large venules. So the large veins are all on the surface of the brain, right? And so you can imagine the direction of the magnetic field actually having an effect if it's perpendicular or parallel to the surface of the brain. So people always said, yes, it will have an effect, but nobody ever calculated what would the magnitude of the effect be. So we saw in our simulations that the magnitude of the effect was dependent on the orientation of the magnetic field. So we calculated this more precisely. For spin echo, it doesn't have much an effect, and that's because the spin echo sequence is actually designed to suppress the signal from large veins and just look at the smallest vessels. The smallest vessels are really in the cortex, and they're randomly oriented. So they're oriented in every which direction, so there's no orientation dependence there. But the gradient echo, that signal is primarily coming from the large veins, and you can see it's strong. It changes by about 40% if your MR signal is perpendicular or parallel. So we thought, this is a huge effect. We should be able to measure this, right? Why has nobody ever measured this? And if you remember, actually, at the beginning of this lecture, I was talking about hypercapnia, right? So the question came to us, well, how would we measure this if nobody's measured this? So we thought the way to measure it is if we could uniformly change deoxyhemoglobin everywhere in the brain, we could then go in, measure the bold signal change at each position on the surface of the brain, and the brain is convoluted, right? So with MR, we can resolve the spatial orientation of the surface of the brain and calculate the angle of the surface normal with respect to the magnetic field, right? So this is a perfect experimental way to investigate how the bold signal would change with respect to orientation with the magnetic field. The only thing is we need to be able to change deoxyhemoglobin uniformly on the surface of the brain. And the way to do that actually is hypercapnia, right? That experiment I was showing you at the very beginning of this lecture. So hypercapnia is pretty much increasing blood flow everywhere uniformly in the brain. That blood flow increase is going to wash out deoxyhemoglobin and essentially change the deoxyhemoglobin signal uniformly throughout the brain. So we could thus go in and measure bold at each point. We calculate the angle with respect to the main magnetic field, and we see, does bold change? Does it depend on the angle with respect to the magnetic field? So we did that, and holy cow, it did. It actually changed by 40%. with respect to the angle. And we overlapped that with the simulation, and we got really nice agreement, right? So this was really cool. We had a validated model that made a prediction that had never been observed experimentally. We went and did the experiment, and we were able to confirm the prediction and learn something new about the bold fMRI signal, right? So this has interesting consequences that with like resting state functional connectivity studies that people are doing with bold, that they are now beginning to realize these are effects that reveal themselves in resting state functional connectivity studies. Okay, so finally, the reason we had set out to do this was to validate the MR estimates of evoked changes in oxygen consumption, right? So people use this simplified model, they measure changes in bold, they calibrate bold, and they assume a relationship between blood flow and blood volume, this alpha parameter. And they want to estimate changes in oxygen consumption. I showed you at the beginning, there's reason to believe that this model here is underestimating evoked changes in oxygen consumption. But we can now use this microscopic model of the bold signal where we know what the true changes in oxygen consumption are. We can simulate the bold and the blood flow changes, put that into this model, and see how accurately we estimate the underlying changes in oxygen consumption, right? So we did this. So if you have changes in blood flow and bold and this is the relationship between bold and blood flow for different changes in oxygen consumption. You get nice plots like this. So we could simulate this with our model. This is for one mouse for different changes in blood flow and different changes in oxygen consumption. We do this simulation for 6 different mice, and we can fit this model to these data, and we get these isocontours here. And from that fit, we estimate alpha and beta. So beta has a value of about 1, actually. So we and others have done a lot of simulations. And remember, this is a physical property of the susceptibility of the MR signal to the deoxyhemoglobin. And lots of evidence suggests that that has a value of 1. So we can just set that equal to 1. This alpha parameter is the blood flow volume relationship. That's usually people believe that has a value of about 0.3, right? Here we got minus 0.05. That doesn't make sense. Let's simplify this model now. Since we know beta is equal to 1, we can just simplify the model. Rick Buxton has done that. And then we can ask the question, how does alpha change with different MR field strengths? Alpha is a physiological parameter. It should not depend on the physical properties of the MR. But we see that actually alpha is changing quite a bit. This is very strange, right? Basically what this is telling us is this macroscopic model is wrong, right? Alpha is a physiological parameter, but it depends on the magnetic field strength. So the model is not accurate in its interpretation of the parameters, but it does fit the data very well. And so if we just can understand what is the right value of alpha to use, we could probably still use this very simple model to analyze our human data, right? And so this is showing if we estimate the evoked changes in oxygen consumption using the standard Davis model, compared with what the ground truth standard 2 is, we underestimate the evoked changes in oxygen consumption. But if we use and this underestimation is pretty much the same underestimation I showed you at the beginning of the talk with the fusion of FNIRS and fMRI. But if we use the optimized model parameters, we can recover oxygen consumption quite accurately. Okay, so this was work actually we set out to do about 20 years ago. Took us 15 years to do all of that work. I was very happy when we finally finished it. And this was hard work by Ted Hubbard and Miriam Musel, Sava Sakadzik with the 2-photon microscopy, Jungwon Lee and Vivek Srinivasan with the OCT, and Louis Gagnon and Xiaoxun Cheng did just outstanding work on the modeling. And if there's any questions, I'd be happy to discuss this at length. I love this work, right? So thanks. Yeah.
Thank you, Professor, for the great talk. Well, in the last slide, you showed us that by changing alpha, you can fit better. You can compensate for the underestimation, but does it retain its physiological meaning or not?
So no, alpha does not retain its physiological meaning, right? The alpha is compensating for other model errors, right? So it's you know, the microvascular network has a very complex topology. You know, the capillaries have lower oxygenation than the veins. That simplified model, of course, is assuming a serial pipe, right? And so it's an oversimplification, and somehow magically, by tuning that alpha parameter, you're able to compensate for that gross simplification of the model.
Okay, so, but is there any hypothesis behind what is alpha measuring, or is it simply it works? And
yeah, I mean, so basically it works. So now we could just do an empirical investigation of how does alpha depend on those physical parameters and try to gain some insight into that. And so that's something we're trying, and others are trying to explore, right? Right, no, it's a nice lesson because, I mean, there's no way we could use a real microvascular model to analyze human data. It's just too complex. So you need to use a simplified model. But the simplified model is always going to have errors, right? So if you can understand what the sources of those errors are and compensate for them, then it allows you to use a simple model to analyze your human data, right? Right. Yeah. Oh, yeah, hi.
Here. Hi. Oh. So I would like to ask, thank you for the presentation first. Did you have already done some of these measurements in some model or animal model or something with neurodegenerative disease or something like that? And if you've done or not, if you think we will be able to predict some neurodegenerative disease or early detect with by calculating the oxy and deoxy and all the things.
Yeah. So we are using this to look at models of Alzheimer's disease and brain trauma as well, and stroke. And so we're using the OCT measurements of blood flow changes and the 2-photon microscopy measurements of oxygen delivery to really understand all of this. And actually aging, if you didn't know, aging is a disease. So don't age. Your cerebral your capillaries are pruning, and the capillary density decreases, and the efficiency of oxygen delivery to the brain is changing. It's all very unfortunate. So try not to age, right?
Okay, thanks.
Right.
So I was curious, in this octopus system that you showed us on one slide, what are the challenges in doing multiple kinds of imaging modalities simultaneously? Is it getting them simultaneous, or do they interfere with one another? Can you speak to that briefly?
Yeah. It just becomes more complex. I mean, the optics, if you design the optics well and then build it, it should all work reasonably well. At the end of the day, with that first system, that OCT and the 2-photon microscopy, when we built it, we weren't great optical designers. We're better now. And kind of the problem we had was optimal focus for the 2-photon was not optimal focusing for the OCT and vice versa. So with that first system, doing them simultaneously just never really worked, right? So we would do one, and then we could tune it for the other, and we could do that, right? So I think now that we're better optical designers, we're building a system where we can get optimal focus for both, right? So it's always surprises like that come up, right? And I would say, right, of course, it's the complexity is not just the sum of the complexity of each. It's actually super linear. It gets exponentially more complex. So if you don't have to combine things, don't combine things. Right.
Thanks.
But there is a lot of power if you do combine it, right? So. Right.
Okay.
Yeah.
No more questions. So
Yeah.
thank
All
you,
right,
David.
Thanks. Yeah.